Hello, everyone. The time has come. The very last speaker of the day, and I'm pretty excited for this.
Me too. And I think I have good reason to be excited, and you do too. Randall Carlson. This man, as I think anyone who has attended the Cosmic Summit in the past already knows, is truly a wellspring of knowledge. I first met Randall, gosh, it was close to a decade ago. I think we were in Minneapolis, Minnesota.
Yeah, what about a decade?
You and I knew each other for about a decade, or have known each other. More than a decade now. See, his memory is better than mine. You're going to find out how good his memory is here in a moment. And I remember Randall told me, he says, you know, I do an event up in the mountains at our friend Julie's house. He says, come on out there sometime and you know, you'll see the talk. And I thought, oh, you know, it's a nice informal thing. And we go back into this beautiful atrium in the back of the house. Randall has a full presentation. They have a projector, and he spoke for 4.5 hours, right, about the evidence for an ancient catastrophe where we had massive flooding that occurred in North America. He shows the geological evidence, the proxy evidence for this, traditional knowledge, mythology, built this case. And I had been thinking for the longest time prior to this, I thought, you know, I'm looking for the next thing. There's got to be something. You know, I'd read the books by Graham Hancock. I'd read all these incredible books by many of the authors present here, Robert Schoch and others, and I said, what's going to be the next thing? What's going to be the next thing? I left that house that night and I said, that's the next big thing. This guy is incredible. And of course, he has gone on to be on all of the major podcasts. You've seen him on Joe Rogan. You've seen him all over the place. I'm so happy to welcome him here to the stage tonight at Cosmic Summit 2025, the legend, Randall Carlson.
Thanks. Sitting back there, I couldn't understand what he was saying about me, but hopefully it was on the good side. Yeah, so I think without really delay, we're going to just get into this. Let me see what we're seeing up here. Okay, good. So what I'm going to do is, how many of you ever heard of the Indian, he wasn't Indian, but he was an artist who visited 120 tribes during the 19th century, painting and writing about them, George Catlin? Anybody heard about George Catlin? Okay, so he, after years and years of visiting the various native peoples, he collected information on their customs, their rituals, their languages, their ceremonies, and so on. He wrote his final book, which was the last rambles amongst the Indians of the Rocky Mountains and the Andes. And at the conclusion of these many, many years and decades, he wrote at the conclusion of this book, which was one of a number of his books, he says, I'm going to quote from the book because it's quite interesting. We're going to use that as the jumping off point. He says, the American Indians are as distinct from all the other races of the earth as the other races of the earth are distinct from each other. And both in the North and South and Central America exhibit but one great original family type. Some writers have advanced the belief that South America and the continent of Europe were anciently united, which is interesting for him to say back, 150 years ago, and that the American continent received its population in that way. But as this is mere hypothesis, it refers us to Bering's Strait, by which route, if the American Indians would spread over the uninhabited but desolate country, several thousand years would have been required to populate and move through the vast regions of Siberia to Bering's Strait, a distance of more than 10,000 miles. And from Bering's Strait to Central and South America and Tierra del Fuego, 10,000 miles more. And an equal of time required, 1,000 years at least, for a civilization to arise sufficient to have built the splendid monuments of the Yucatan, and the vast space of time that has transpired since those monuments were depopulated. In all, a space of time far transcending that allowed by sacred history or even by geology for man's appearance on the earth. The American Indians seem to know nothing of this, yet their traditions and monuments prove beyond a doubt their great antiquity. 4 of 120 different tribes which I have visited in North and South and Central America, every tribe has related to me more or less distinctly their traditions of the deluge, in which 1 or 3 or 8 persons were saved above the waters on the top of high mountains. Some of these tribes living at the base of the Rocky Mountains and in the plains of Venezuela and the Pampa del Sacramento in South America made annual pilgrimages to the summits where the antediluvian species were saved in canoes or otherwise, and under the mysterious regulations of their medicine men, tender their prayers and sacrifices to the Great Spirit to ensure their exemption from a similar catastrophe. Indian traditions are generally conflicting and soon run into fable. But how strong is the unanimous tradition of the Aboriginal races of a whole continent of such an event? How strong a corroboration of the Mosaic account? And what an unanswerable proof that the American Indian is an antediluvian race. How far these general traditions of a flood relate to a universal deluge or to local cataclysms, of which there have evidently been 1 or more over portions of the American continent, or whether there has been a universal deluge and at what period, it is difficult to determine. One thing, however, is certain. The Indian traditions everywhere point distinctly at least to one such event, and amongst the central and southern tribes, they as distinctly point to 2 such catastrophes in which their race was chiefly destroyed. And the rocks of their countries bear evidence, yet more conclusive, of the same calamities, which probably swept off the populations in the plains, and as their traditions say, left scattered remnants on the summits of the Andes and Rocky Mountains. Since that epoch, their descendants have wandered off into the fertile plains where climate and a greater abundance of game and fish have invited them, peopling in time the whole continent, from the Atlantic to the Pacific coasts and the West India and other islands. Now, I'll mention that, modern science now has pretty much confirmed the indigenous traditions. We now know there was a culture called the Clovis that seemed to exist 3 or 4 centuries just prior to the Younger Dryas boundary. The evidence would suggest that this culture almost entirely disappeared. Of 50-some Clovis sites known around North America, unglaciated North America, virtually all of them appear to have been depopulated right around the time of the lower Younger Dryas boundary. We know also that in the aftermath of the Great Ice Age, in a period called the climatic optimum, also called the hypsothermal, the climate from roughly 10,000 years ago to about 6,000 years ago was warmer than now, actually warmer than now. And you had an environment in which the top predators, the top of the food chain, had been largely depopulated. There was no more giant cave bears. There was no saber-toothed cats. There were no more dire wolves. The list goes on of these predatory animals that had been the top of the food chain. And so you had a proliferation of small game. With the warmth and the rainfall of the hypsothermal, you had a very prolific ecosystem lasting for a while. And it looks like the model now is very similar, if not identical, to the stories of the Native Americans, that their ancestors were largely succumbed to the deluge, and then in the aftermath you had scattered tribes which then gradually repopulated the continent. And we find similar traditions from all over the world. A couple more details they say here, and this is interesting. Amongst all of these tribes, as well as amongst the present Mexicans and the numerous tribes to the north, even to the Kiowas and the Comanches, I have found distinct traditions of 3 successive cataclysms, 2 by water and 1 by fire. And in the rocks and mountains, both in the West India Islands and on the Mexican coast, as well as in the Yucatan and its ruins, I have found, from chemical and geological tests, undeniable evidences of the same catastrophes. And there we can go to the slides now. So what I'm going to do in this PowerPoint show is I'm going to look at some of that geological evidence for great diluvial events or deluges in the North American continent. And hopefully going out of this, I'm going to try to confer upon you the ability to see things that you may have already seen in abundance, but not understood what you were looking at. So the idea here is I am going to try to teach you a little bit about the language of geomorphology and geology, and to give you the ability to understand that this phenomena is all around you. Let's go to, we'll go to slideshow mode right here. I'm good. All right. So this book, if you're interested in it's a very interesting read. You can download it. It's in the Google Archives. You can download it in PDF form for free. Last Rambles Amongst the Indians of the Rocky Mountains and the Andes. This one was published 1867. So let's get in and look, divert a little bit. We'll look at some of the modern ideas about floods and where they might have come from. So this was from a 2009 Geological Society of America annual meeting, and the subject of this particular paper was glacial megafloods. So megafloods, which are terrestrial water flows with discharges exceeding 1 million cubic feet per second. It's a lot of water. So 1 million cubic meters per second. So there's roughly, say, 35 cubic feet in a cubic meter, so you can kind of get a sense of the scale here. This is an enormous amount of water. And they are the largest known freshwater floods, with flows comparable in scale, though of shorter duration, and ocean currents. Although there are no modern examples of megafloods, and thankfully for that, because if there were modern examples of megafloods, we might not even be here right now. But it's important to bear in mind that we're looking at a phenomenon that's very distinct from anything we've experienced in modern historical times. Although there are no modern examples of megafloods, such flows occurred during major periods of glaciation. A prominent example is the paleoflooding caused by late Pleistocene outbursts from glacial Lake Missoula, which formed when the Purcell Trench lobe of the Cordilleran ice sheet extended south from British Columbia to the basin of modern Pend Oreille Lake in northern Idaho. Now, many of you have heard my lectures and been on tours and stuff where we've gone out there, explored exactly this region, and seen, again, so that people can see for themselves the magnitude of some of these diluvial phenomena. The ice thereby impounded the Clark Fork River drainage to the east, forming a lake extending into western Montana with a water volume of about 2,500 cubic kilometers, which is roughly about 620 cubic miles of water. That's a lot of water. If you can picture an ice cube that's 1 cubic mile, a square of 1 square mile, and then a mile high, okay, imagine now 600 of those. And then it's suddenly released. Now, I have issues with the current ice dam model for multiple reasons, and I don't think that actually glacial Lake Missoula was the ultimate origin of these megaflows. We're not going to get into that too much today, because I've got probably way more material here than we're going to be able to get to before dinner time, right? And I know once dinner time hits, you guys are going to be headed for the door. So the largest Lake Missoula outbursts were in the range of 10 to 20 sverdrups, and a sverdrup equals 1 million cubic meters per second and involved flows that lasted for several days. Okay. The Missoula floods were responsible for generating the channel scabland of east central Washington state. A complex of anastomosing, which simply means branching. An anastomosing pattern is when a flow of water, like a river usually, bifurcates or separates into multiple flows and then rejoins. And so it creates this plexus of divergences and convergences. And that's simply what we mean by that mouthful of a word, anastomosing. Just think a branching river, okay? A complex of anastomosing rock-cut fluvial channels. If you remember, I think when we were up on Pilot Mountain, I gave a little talk, and the difference between the three terms here that are relevant to the topic we're talking about here. Fluvial, think FL, flowing. It means flowing water, or flowing liquid, but in this case, flowing water. Alluvial is the material that's deposited by water. Actually, alluvium is the material deposited by flowing water. Pluvial means rainfall. So if you have pluvial, or pluviation, if you have a pluvial event, you will then have fluvial consequences and ultimately alluvial, okay? So I'm going to be testing you all randomly to see who remembers that. So these flows deeply inundated the Columbia Gorge and the Willamette Valley before discharging into the eastern Pacific Ocean. Other late glacial megafloods occurred along the margins of the great ice sheets that formed during the Pleistocene in North America, Eurasia, and southern South America, as far south as Patagonia. River basins connected to these ice sheets were impacted by the flooding such that invasions of water changed drainage patterns, enlarged valleys, and delivered huge fluxes of water and sediment to the oceans. Numerous spillways were flood integrated into temporary rivers in parts of North America, such as the St. Lawrence, Mackenzie, Yukon, Mississippi, and Columbia. I'll mention also the Missouri River. And Eurasia, such as the Ob, and I'm not sure how to pronounce this, the Irtish, Yenisei, Volga, and Dnieper rivers. The late Pleistocene megafloods are associated with a broad range of hydrologic and climatic changes that are only now being fully understood. So water plays a dominant role in many glacial processes, and the erosional, deposition, and climatic significance of meltwaters and associated fluvioglacial. Now there's another one. That simply means the combination of water and glaciers working together, okay? Fluvioglacial processes cannot be overemphasized. At its maximum extent 20,000 years ago, the volume of the Laurentide ice sheet was 33 times 10 to the 6th cubic kilometers. So that's 33 million cubic kilometers of ice. So to get a perspective here, that's about the same as the volume of all the ice present today on planet Earth. However, this is just talking about the Laurentide ice sheet. There was also the Cordilleran ice sheet, which was about the size of the Greenland ice sheet of today, and there was the Fennoscandian ice sheet, which was about double the size of the Greenland ice sheet. So that was a whole lot of ice, way more than double the amount of ice that's on the Earth today. So obviously, it's a very different world. And as a result of that, very important, we were discussing, so we had a very interesting conversation earlier with Michael, who did the documentary on Atlantica, and Robert was there and had some very interesting critiques of Michael's work, but some of the things that came up were the idea of, we didn't really get into it, but one of the important factors was sea level rise, because sea levels were lower during the late glacial maximum than they are now by at least 400 feet. And then by geological timescales, the rise of sea level to modern levels was very rapid. And in fact, the evidence now suggests it was not a continuous process, but was actually pulsed with at least two major meltwater pulses, one occurring at about 14,600 years ago and another one occurring about 11,600 years ago, which in the discussion of Atlantica, that date is interesting because that precisely corresponds with Plato's dates in his dialogues, Timaeus and Critias, that he gives for the ultimate subsidence of Atlantis. So anyways, pulses of meltwater flowing to the Atlantic Ocean from large ice-dammed lakes altered thermohaline circulation. That's basically just the movement of ocean waters. There's been some concern now that melting Greenland ice is going to cause disruptions in the thermohaline circulation. I don't consider that a factor, only because when we look historically, we see that the discharges at the end of the last ice age were orders of magnitude greater than anything that's being introduced into the North Atlantic right now by melting Greenland ice. However, look at this. One such discharge event via Hudson Bay at 8,200 years before present released 160,000 cubic kilometers of water in 12 months. So when we're talking about that kind of scale of discharge into the oceans, yeah, it's certainly plausible that it's going to affect the ocean circulation. But I mean, 160,000 cubic kilometers of meltwater in a year, okay? Global sea levels recovered from glacial maximum low stands reached at about 20,000 years ago at an average rate of 15 meters per 1,000 years, but estimates of shorter term rates suggest as much as 20 meters of sea level rise in 1,000 years, and for short periods, rates as high as 4 meters per 100 years, and I would suggest that sometimes maybe even faster than that. But the point here is that the old models were a nice smooth continuum of sea level rise. Typically, in the older papers, going back to the 50s, 60s, and 70s, the assumption was 30, 40, 50,000 years. It's been shortened to 10,000 years, and within that 10,000 year span, it's clear that the rate of melting and their henceforth sea level rise was not a continuum, but it was pulsed. And that's an important thing that I think in our understanding of this whole process, which raises questions about the nature of the cause of the melting. And there's two, to me, really interesting, powerful ideas out there. And I'm sure that some of you are familiar now with Robert Schoch's work on solar storms and so forth. Very likely could have been a contributing factor to the rapid melting. And at some point, I hope to talk to Robert more about this and how that model might relate to glacial melting. But I'm not going to get into too much the cause today. I'm just going to look at the geomorphology of it so that you can start seeing things for yourselves. Okay, so we'll begin with this, just a map of North America, and then I'm going to show you the Laurentide and Cordilleran ice sheets. And so they were two distinct ice sheets, right? The Laurentide was up to perhaps 1.5 miles or more thick. It was centered roughly over Hudson Bay. And where the thickest ice sheet is now, it caused the greatest depression in the landmass called isostatic depression. And as a result of that, the area around Hudson Bay has been rebounding ever since the ice load was removed. And it was still low enough after the removal of the ice sheet that seawater was able to encroach into the basin, and it is now connected to the North Atlantic. But for a while there, it was a large volume of fresh water from the glacial melting. So the Cordilleran ice sheet was a separate ice sheet, and you can see there's this trough, I guess you could call it, between the two ice sheets. It appears now, early, that during the deglaciation phase, that there was an opening between the two ice sheets that then allowed the migration of both people and animals from Beringia, which was the area from Alaska to Siberia, down through that ice-free corridor to the unglaciated lower part of North America. It appears now that occurred between about 13,000 and 15,000 years ago, and then at about 12,800, between 12,800 and 12,900, was the Younger Dryas boundary, which was a reversal of the more naturalistic warming that was taking place during two stages of the late Pleistocene that were called the Bolling and the Alarode. And there was an older Dryas, we don't necessarily talk about that today, of a much shorter duration, but it was also a cold snap, and then it was followed by roughly 3,000 years of warming, and then we had the Younger Dryas, which was a return to full glacial cold. It's possible, but I don't know, I haven't seen enough data to conclude yet, but it's possible that in that reversal to full glacial cold after a few thousand years of warming, that the corridor between the Cordilleran and the Laurentide ice sheets would have closed up again. I don't know for sure, but this was the configuration. I'm not showing in this slide here, I'm not showing the lowered sea levels. You have to bear in mind, with 400 feet lower sea levels, you exposed a lot more of the coastline. This is the modern coastline. I'm going to redo this graphic, but using late glacial maximum coastlines. But for example, the peninsula of Florida was nearly twice the width that it is now because of the exposed continental shelves. Okay, so in this slide, what I'm doing here is I'm showing everywhere, and this is not all comprehensive, but this is showing everywhere where there may have been documented catastrophic water flows. And there's a bunch of them, and we're not going to obviously look at them all today because we don't have time. But a lot of the ones that I've studied in person would be the Athabasca floods, which is showing this area right here, which is just east of the Rocky Mountain front. We'll come back to that. Obviously, the Missoula floods, the Bonneville flood. In fact, with some of my friends and colleagues, we just took a tour last month of the Bonneville flood, which was peaked at just almost 40 million cubic feet per second. And it was the discharge of Lake Bonneville, a gigantic inland sea, if you want to call it that, that got up to about 1,000 feet deep, actually a little bit more than 1,000 feet deep. And it was, so how many of you have been to Salt Lake and seen Salt Lake City and seen the Great Salt Lake, which varies between about 20 and 30 feet deep? Well, if you're standing there where Salt Lake City is now, during this very short-lived temporary high stand of Lake Bonneville, the water surface would have been more than 1,000 feet over your head. And as you travel north from Salt Lake City, the Wasatch Mountains to your east, you can very clearly see two large shorelines, what's called the Bonneville shoreline and the Provo shoreline. And what happened is at the north rim of this lake, and if you look at the whole area, which I'm going to show you right here is this area. There's no, I'm sorry, right here, here it is, right here. It's called the Basin and Range Province, and it has no outlets to the ocean. So any rainfall that falls over the Basin and Range Province now essentially just is absorbed into the ground and evaporates very quickly because it is basically a desert environment. So now, when you look at the Basin and Range Province, there's evidence that during the late glacial maximum, there were huge lakes all over throughout there, which tells you that the environment was drastically different from what it is today. Anyways, we spent a couple of days touring the area of the Bonneville Basin, and what really blew my mind was how enormous the basin was. To travel for 2 days and we only saw a part of it. And then you're basically traversing over desert floor. And then to realize that this lake was 600, 700, 800, even up to 1,000 feet deep, where it's just desert now. Clearly, a very different environment, okay? So this is just a few of them. I've got also the southern Appalachian pluvial floods. Pluvial because I think they were caused by rainfall, and I'm going to show you some of the evidence in the field that you would look for. Let's see. So catastrophic flooding will begin in western North America outside the Bonneville and the Missoula basins because I've talked so extensively about those two already. I've got lectures online. I've taken, 6, 7 tours out there, covered actually thousands of miles of that terrain. So I'm not going to talk about that too much here. And we'll skip the glossary for catastrophists, but there, look at the first one, alluvial, pertaining to or composed of alluvium, or deposited by a stream or running water. And alluvium, alluvial fan. So if you've got a mountain channel, water gushing through it, picking up material, it discharges from the mouth of the canyon. When it spreads out, it loses competency to transport material. That material is then deposited and it forms a splayed out feature called a fan delta, particularly if there's already water there and the discharge is carrying sediment, it will build this fan delta. And for example, New Orleans is built on a massive fan delta. in the Gulf of Mexico that was transported by megafloods coming down the Mississippi River that were then the result of massive rapid melting of the Laurentide ice sheet. All right, but let's just keep going here. So we'll go through this. This is the types of landforms that you would look at if you're going to be a diluvialist and you want to learn about how to actually go out on your own and see some of these features. These are the things you would study and learn. We'll go down very quickly. Through erosional forms, you would have scabland type terrain. You would have butte and basin topography. We saw an example of a butte, or similar to, not to say that it's a butte, but typically a butte, if you recall from our visit to Pilot Mountain, I said that a butte is about as wide as it is tall, right? Pilot Mountain kind of fits that. So it's the scale of a typical butte. If it's wider than it is tall, it's a mesa. If it's wider still, it's called a tableland. If it's narrower, it's called a pinnacle. And if it's got a flared top, it's called a pedestal rock. All of these things, I think, are the results of erosion. Okay, oversized stream and river channels. I'm going to show you examples of those. Coulees and spillways. A coulee is like a river channel, except there's no significant flowing water in it. There's little to no flowing water. Moses Coulee, Grand Coulee are two spectacular examples of coulees out in Washington State that one explores when we're looking at Missoula flood phenomena. Strand lines and shorelines, I just mentioned the Bonneville shoreline and the Provo shoreline on the Wasatch Mountains that are very distinct. So that's one of the things you look for. Strand lines are typically just fossil shorelines. And I will mention, go back to the Bonneville flood, that there was no outlet to the ocean, right? Except until that water rose up to about just under 1,100 feet. There was a low saddle on the north extent. There was a bay, a north extension of the lake. The lowest point on the shoreline of the lake was right at the peak, the northernmost peak of that bay. And it's a place there now called Red Rock Pass. And apparently there had been at one point a landslide that filled this pass with about 350 feet of material, right? So this is relatively young, so it's unconsolidated. It is not lithified into rock, right? Apparently Lake Bonneville rose up and stabilized temporarily at this level, and there was an earthquake. The earthquake may have been a product of this massive volume of water that had accumulated in the basin. Anyways, it looks now like there was an earthquake. This 350 feet of material from the landslide gave way, and it took about, estimates are from a few weeks to a few months, for half the volume of lake to drain out through this pass. It dropped 350 feet and stabilized at a hard, I think it was a granitic sill, which was not easily eroded. So the lake dropped 350 feet, and then it etched or carved a second shoreline so that you can see these two shorelines on the mountainsides, right? It stabilized there, and then at that point, shortly after, the whole area transitioned to desert, and over about a period of about 3,000 years, the remainder of giant Lake Bonneville evaporated away and left Great Salt Lake, which is a mere puddle left over. Okay, so dry cataracts. Imagine Niagara Falls with no flowing water, and that's essentially a cataract. And what happens is the flowing water spills over the rim, and depending on the force, the shear power of the water, it will eat upstream the cliff of the cataract. And so that becomes, you call that a receding cataract. And that's one of the remnants of large floods, is when you see these cataract or horseshoe-shaped features in the landscape that either have no flow or very small streams and creeks flowing in these very large horseshoe-shaped features called cataracts. So that is one of the more spectacular of the types of evidence that one would see for deluges. And then buttes, pinnacles, pedestals, I've talked about those, and then potholes is another one, because when you have very turbulent waters, it'll create vortexes. And those vortexes can be highly erosive, especially if they're picking up material, and it literally becomes like a power drill, and it can drill into bedrock. And it leaves behind potholes, some small, some medium, some very large. And I'm going to show you examples of those. Now that's all erosional. Now depositional, you have large gravel beds and bars, you have boulder streams and block fields, so you might have an area of many square miles that are just covered in boulders. And how did they get there? Well, they were deposited by moving water. Large erratic boulders. You can have erratics that are moved and deposited by ice or by water, right? Alluvial and debris fans, fossil lake beds, giant current ripples, imbrication. We'll see some examples of that. To understand imbrication, imagine a row of books on a bookshelf stacked up, and if I push it like this, the books will tilt, and they will stack up like this, see? If I push this way, they're like this. Water will do the same thing to rocks and boulders, and it will stack them up in a very distinct pattern that once you've seen it, you learn to recognize it. It's readily evident that that's what it is. It was a function of water flow, and this is called imbricate structure or imbrication, right? And I'm going to show you examples of that. And then you have several things that are sort of it's hard to separate which part is erosional and which part is depositional, and that would include drumlins, eskers, tunnel valleys, terraces, and benches. We're not going to have time to get into all of this today. I am going to show you some drumlins, though, because I think drumlins are one of the keys to understanding the origin of these great deluges. So let's just get in. We'll start looking at, this is called colossal foreset glaciofluvial gravital deposits in the Fraser River Valley in British Columbia. This is a series of pulsed flows coming in from the right, and what we have is it's called the dip, the tilt, essentially, of the sediments that have been deposited. The tilt, or the dip is the term, is down in the direction of the current flow. So in this diagram here, we're looking at flow from the right to the left. And this flow, which rightfully called glaciofluvial, was a product of both glaciers, originally probably grinding up and creating the rough material. Then you had water flows that sorted it into these tilted strata of layers that you can see here. All of this flowed down into the Fraser River Valley, spilled out into the Pacific right where the city of Vancouver now is. It built a delta fan, or a fan delta, and the city of Vancouver is built upon that, very similar to the way New Orleans is built upon a fan delta down in the Gulf of Mexico. Portland is also built on a delta. So in parts of New York, like I've heard from builders in Portland that when they go to excavate a basement, they find huge boulders embedded in the soil. Okay, so this is, I think the first thing we'll look at is what's called the Big Rock, and it's also part of a feature called the Foothills Erratics Train. So what we're looking at here is some of the eastern Rocky Mountains, and if you look right here, this is in Jasper National Park, and this is a mountain called Mount Edith Cavell, and there's a string of mountains here that's made of a certain kind of very distinctive metaquartzite, which is a metamorphic rock. And all of this area that you're seeing here, if you go back to the LGM, or late glacial maximum, was buried under a massive mantle of ice. And what it would have looked like if you would have flown over an airplane 15 to 20,000 years ago is that what it would have looked like. The Rocky Mountains would have been buried, and only the peaks of these mountains would have been elevated above the ice sheet. They're called nunataks or nunataks, isolated mountain peaks rising above the Greenland ice sheet today. But you would have found this very same thing over the Canadian Rockies, very similar feature to that. So there was a massive amount of glacial ice that is now gone, and it melted, and when it melted, it had to flow somewhere. And I'm arguing that it flowed to the south, and what was ultimately responsible for both filling what we call glacial Lake Missoula and carving the channel scablands. So now the reason I showed you this and this Mount Edith Cavell and mentioned the metaquartzite is that there's a feature called the Foothills erratics train, where this is showing here. This would be roughly where the headwaters of the Athabasca River are. And it shows where melting water from those glaciers would have poured out and then flowed south along the eastern flanks of the Rocky Mountain front, ultimately discharging into Montana. Well, one of the things that happened is along this route, there's hundreds of these very large boulders of the same type of rock lithology that you find at Mount Edith Cavell, right? So the largest of these is called Okotoks, which is Blackfoot for big rock. And it's estimated to weigh about 18,000 tons. And it sits out on the western prairie just east of the Rocky Mountains. This is just samples of some of the boulders that are, again, there's hundreds of them, that reach from where the Athabasca River discharged from the Rocky Mountain front. And then you'll notice, if I were to go back and show you the ice-free corridor, it's interesting that the Foothills erratics train defined almost perfectly the ice-free corridor. But here's the interesting thing. They were ultimately sourced from this Mount Edith Cavell. If you ever go to Jasper Park, it's a spectacular mountain. On the south of this type of rock, Edith Cavell, on the north end of it is Mount Robson. And so this mountain range in there was the source of this Foothills erratics train. Well, and then so here we have some examples of the rocks that are, sitting along define this pathway. So here's the question: how did they get there? All right, let's see if we can find okay, so there's Mount Edith Cavell, or Cavell, I think it's Cavell. Here's another view of it. You can see what's called a cirque up here that was once completely filled with ice. And again, during the late glacial maximum, only the peaks of these mountains would have been clearing the ice sheet. And here is Okotoks, the big rock, sitting out on the western prairies of Alberta, just south of Calgary. And here's another version of it where you can really see how big it is. Now, this is actually somewhat distinct from normal glacial erratics because the distance of transport was over 200 miles. Yeah, the 18,000-ton behemoth was transported nearly 200 miles from its source at Mount Edith Cavell. Okay, so normally, if it's in 200 miles, let's say that typically a normal pace of glacier movement is going to be anywhere from a few feet a year up to a few miles per year, unless it's in a surge, which is only a temporary condition usually. But it would have taken hundreds of years if this was transported by glacial ice. In those hundreds of years, you would have had, on average, up in that area is about 4 feet of snowfall per year. So this rock right here, for example, would have been buried under hundreds of feet of glacial ice. The question is could this rock survive passage intact from transport within glacial ice? And the answer is, I think, a resounding no, because if you look at this rock, you'll see that it's several things you'll take to note about this. It's got sharp corners, right? Glaciers tend to cause gouging and striation. They grind off the corners. These have sharp corners. And the original rock was one piece, and here you can see it's 3 pieces. And also, you'll notice the height of this thing here is about 20 feet above the ground surface, right? Maybe even a little more. This ground surface is alluvium. And at the time that this Okotoks was left here on the prairie, the ground was soft enough that the rock sank into it. It's not really sinking now. The ground is dried out, it's hard, it's consolidated. But when it was deposited, the ground was apparently soft enough that it sank. When it did, the fractures in the rock became more obvious. The question is how would you transport this by glacier over 200 miles or up to 200 miles and still have this rock arrive more or less intact at its destination? And I think the answer is, and now having looked at dozens and dozens of examples of large-scale erratics throughout eastern Washington that were brought to their place of deposition via iceberg rafting, right? There are many examples that I've shown in my slides and drone footage and tours and stuff. We look at many examples of these huge, huge rocks that were transported via iceberg rafting, right? So now the question is, when you have an 18,000-ton rock and you have an iceberg transport, you're looking at an iceberg that's probably the size of a tanker ship, right? Now, if that's the case, and I think that and again, I'm going to have to gloss over a lot of the field evidence and data and so forth, just to get to sort of the conclusion here is that, number one, it would require transport on an iceberg. That iceberg then had to be carried in water, right? So now the question comes, 18,000-ton rock, what size iceberg? A very large iceberg. Now, how much water would it take to float an iceberg basically the size of a tanker ship? And this is where this gets interesting, because when you look at the discussion of say, the origin of the Missoula floods that created the Channel Scablands, there's no reference in the literature to it being related genetically to this flood. But here's some interesting other data. Mount Edith Cavell and Mount Robeson and that whole range of mountains is on the western side of the Continental Divide. Here you've got a big rock that's sitting on the eastern side of the Continental Divide. So you've got some challenges there, how you transport that rock. Well, let's consider. You've got to have the rock, and in fact we know there's hundreds of these metaquartzite boulders in that line, 500 miles from the mouth of the Athabasca River down to across the Montana line, over 500 miles. And there's hundreds of these boulders, right? They were probably all transported aboard icebergs. So now you have to have a mechanism whereby you can fracture perhaps earthquakes, perhaps seismic shaking, perhaps something else. Something, though, where you can fracture large chunks of the boulders from the mountains, the flanks of these mountains, the shoulders of these mountains, load it onto the ice, fracture the ice while you're simultaneously melting the ice, and now you've got the water, you've got the icebergs, and you've got the boulders. So what this does to me is creates a very interesting paradox of trying to explain that and what ultimately was the trigger. Well, whatever it was, I think clearly we can assume that it was catastrophic. Now, what are the dating of this? Well, the dating is not precise, but it looks like I've seen dating ranges between 12 and 15,000 years ago. So it puts it very much in that window. Now, was water involved? I think that a piece of evidence that suggests that the water was involved, various copious amounts of water, was when you get to the southern end or terminus of the erratics train. This is what you'll see like from Google Earth. So I don't know if you can tell this, but these are gigantic current ripples. And those current ripples have wavelengths of about 1,000 feet or more. They're not really high, 30 or 40 feet, so when they're 1,000 feet apart, you don't really see them from the ground. But when you get up above and look down, that's when you begin to see. And I would say that current ripples on this scale are very anomalous. They're not something that we see occurring today, but if we look at the deposition of an 18,000-ton boulder out on the prairies of Alberta, that's also anomalous. Not that we don't see phenomena like that happening today. So I think that these are part of two expressions of a singular event. The water that transported those icebergs with their cargo of big rocks also created the current ripples that you see here. And ultimately what that led into, you can see the current ripples are right here. Where that water ultimately ends up is becoming the headwaters of the Missouri River. And we followed several times the routes of the Missouri River, and you can see that there's very clear two scales. There's the modern river, and then there's the ancient mega river. And if you look at this, it shows very clearly, because what you're seeing here is the modern Missouri River flowing on the bottom of this channel, and you see two embankments, right? One on the south, one on the north. That, I would argue, was the mega river that carved the channel that the modern Missouri now flows in. And that mega river would be on a scale sufficient to account for the flows that not only created the giant current ripples, but also deposited the great erratic boulder train. So then we're coming farther to the east. This was Alan Kehew and James Teller, who've done tremendous amount of work related to post-terminal glacial megafloods. James Teller has just recently done work showing that there were catastrophic megafloods flowing north into the Arctic Ocean that date precisely at the bottom of the Younger Dryas at about 12,850 to 12,900 years ago. Check out, you can probably find some of his papers online. Look up James T. Teller if you're interested in diving into this stuff deeper. Anyways, in this particular paper, glacial lake spillway incision and deposition of a coarse-grained fan near Watrous, Saskatchewan. Appeared in the Canadian Journal of Earth Sciences, so we're not going to quote a lot from it, but here's the general idea. The legacy of catastrophic drainages of proglacial, meaning in front of the glaciers, proglacial lakes, is a characteristic suite of erosional and depositional features. And I went through the summary of erosional and depositional features. Spillways generally lack deposits from the floods themselves because of the intense erosion that accompanied lake drainage. The size and morphologies of these channels are the best indication of magnitude and duration of these events. So all from the Rocky Mountains to the Great Lakes, there are hundreds of huge spillways out in the prairies that are all meltwater produced. And a lot of the rivers that flow now occupy these ancient fossil giant channels. The morphology of this one particular spillway that they're studying here is similar to many proglacial lake spillways in the mid-continent prairies of Canada and the United States. These channels were rapidly incised by erosive flows of high discharge. Despite the problems in quantifying the characteristics of glacial lake outbursts, the channels and deposits themselves provide confirmation of the impressive magnitude of these events. Going on, another Mark Lord and also Alan Kehew, going back to 1987, sedimentology and paleohydrology of glacial lake outburst deposits in southeastern Saskatchewan and northwestern North Dakota. Glacial lake outbursts occurred in the northern Great Plains as ice marginal lakes suddenly drained, forming an interconnected system of glacial lake spillways. The outbursts were highly erosive. This is an example of a fan, a giant boulder bar in Saskatchewan left over from catastrophic meltwater floods that were dated to about 12,000 years ago. And you'll see many examples of this if you travel. Just piles of boulders strewn out over the landscape, and that is going to be a certain indication. Let's keep going here. Let's proceed. Okay, so here is a bathymetric model of eastern basin of Lake Superior. And what you see there is a series of huge gouges, much like the coulees of the channel scablands of eastern Washington. I would argue that these were formed by subglacial flows of enormous pressure and enormous volume that discharged to the south, flowing from the north to the south. And we'll come back to that. I'm just going to show you, jump off Earth over to Mars for a second so that you can see what we call streamlined erosional forms. And this was actually, what's interesting is because the paleohydrology that we've been studying on Earth is leading into insights into the hydrology of ancient Mars, right? So we're learning a lot. And then what we're learning from Mars, we can transplant back to Earth. So let's see, this is Athabasca Fluting Field, Alberta, Canada, implications for the formation of large-scale fluting, erosion lineations. Now, the most likely explanation here is that you've got enormous floods, and in these floods, moving over the land, you've got lots of icebergs and broken chunks of ice. Those icebergs are scraping along the bottom of the flow. And as a result, you can see here these linear features. Sometimes if you're out driving, I know there's something similar to this up in northern Minnesota, and I remember as a kid driving, and the roads were running perpendicular to these parallel flutings, they're called. It was like this, and I used to wonder, why are we going up and down, right? But now I understand what happened there. So let's just move on. We're going to do this quickly. This is looking out over a dry, giant riverbed. My slide here, this was just after they started with the security stuff, and I went through the early versions of the, you know, when you're going through security at the airport, and the x-rays or whatever they were obliterated my slides. But this is showing the direction of water flow, and this is an aerial satellite photograph where you can see the giant ripples. And again, you don't hardly see these from the ground, but they're there, and it shows that you had massive flows of water. Let's see here, we'll go to this one. Again, all of this down here is called bed forms. What's interesting here is you have this very pyramidal shaped mountain. Well, this can also be a consequence of water erosion. And I've seen many examples of almost perfect pyramids within stream channels and so on that I know were formed by water flow. But if you look at the texture of the ground here, these are called, in the lingo of geomorphologists, these are called bed forms. And again, they were produced by water flows probably at the end of the last ice age, when there was an enormous amount of rainfall over this area, and now they're just basically fossil features on the desert floor. This dark green here is Death Valley, and there was a whole series of flows into Death Valley, which sits on the southwestern rim of the Basin and Range Province, which is also included Lake Bonneville. Interestingly, right around the time that Lake Bonneville was filling up, Death Valley filled up with a lake called Lake Manly, and like Bonneville, it was over 1,000 feet deep. And of course, it's completely just dry, hot, barren now. How many of you ever been through Death Valley? If you've been through Death Valley, you probably weren't thinking about the fact that once upon a time you would have been on the bottom of a 1,000-foot deep lake that is where Death Valley is now. But we find these kinds of examples over and over and over again. Here's a beautiful example of a fan delta. So this is in Death Valley. This is at Mormon Point. There's a highway, so you can drive along this. And you can see the discharge. You can see very clearly that the fan splayed out here is formed of material that was eroded in the cutting of this channel. But if you look carefully, you'll see that there are remnant shorelines up here. And those are left over from Lake Manly. So the question is when did I think the sequence of events here is you had Lake Manly, and that meant that there was a lot of water flowing into Death Valley, okay? Then as the climate changed and it shifted over to a desert, arid environment, the water began to evaporate. And as it downcut, it created this channel and splayed this fan out here. But here's the interesting thing. If you go up, and I've hiked up here in these gullies, and what you see up there is even the gullies themselves of this larger feature right here are water deposited. So what it appears is that this whole feature was a delta that was formed in Lake Manly. Then Lake Manly dried up, evaporated away, left a series of declining shorelines, and then the modern regime cut this gully into the unconsolidated sediment of this large sediment accumulation here, and then created the modern delta. And if you look closely here, you'll see that this is actually the modern flows right here. It's very minuscule, and it gives you an idea of the scale of these and the changing scales of this phenomena. Yeah, there's an arrow pointing to and just a series of examples of other fan deltas that are produced. So here's a deeply trenched and eroded alluvial fan on the west base of the Panamint Range in California. And what you can see, again, look there, you see those horizontal lines? Those are shorelines. So again, what we're seeing here is the massive work of water flows, but there's virtually no water there now. Okay, are you starting to get some of the pieces put together? Let's just keep going here for the sake of time. Okay, so this is a good one, somewhat old, from 1963, and yet it's worth looking at here. The origin of alluvial fans in the White Mountains of California. Deposition by perennial streams on White Mountain alluvial fans appears to be of minor significance. He's talking about at present. Streams in the area appear to accomplish little erosional or depositional work during periods of normal discharge, either within the mountains or on the fans. Their theoretical capacity for load may be high, but the caliber of most of the available debris is such that they are incompetent to move it. In other words, whatever built these fans, they were created, and now they're fossil features, and the modern flows really aren't affecting them, hardly at all, right? So again, evidence of two very distinct regimes of flow. A notable morphological characteristic of many of the White Mountain fans is the presence on their surfaces of large boulders far from canyon mouths. These are particularly conspicuous in the northern part of Upper Owens Valley. The largest boulder discovered is on the Marble Creek Fan. The massive granite block measures 30 by 25 by 25 feet and has an estimated weight of 1,500 tons. The location of such huge blocks has stimulated much speculation about how they could have attained or how they could have arrived at their present sites. And this is an old black and white photograph of one of those large rocks. You can see the geologist standing there for scale. What they had to say about it is this: alluvial fans on the White Mountains, and by analogy, those of other Great Basin ranges, appear not to have been built by the ordinary processes of stream deposition. Instead, spectacular episodes of debris flow deposition have been irregularly interspersed with periods of quiescence. This is very important. During intervals between major rubble flows, morphologic changes on the fans have been minor. In the Great Basin environment, the spectacular seems to have been the normal, for it is by spectacular processes that a large share of the grand work of gradation has been carried out. And then we'll talk about Afton Canyon briefly. It's a 150-meter, that's almost 500 feet deep canyon that formed as a result of overflow and drainage of Lake Mannix, an approximately 215 cubic kilometer Lake Wisconsin pluvial lake, pluvial meaning it was formed by rainfall, right, in the central Mojave Desert. Stratigraphic and geomorphic evidence suggests that Afton Canyon was cut rapidly sometime after 14,230 plus or minus 1,325 years before present. The rapid drainage of Lake Mannix and subsequent basin dissection have important implications for late Quaternary lake fluctuations in Death Valley. And this is what you see when you travel through Lake Manning. The Afton Canyon is mountains of alluvium near the entrance to Afton Canyon in the Mojave Desert. Watch my Squaring the Circle podcast I did where I'm talking about Egypt and erosion in Egypt, and I show parallels between features in Egypt and features that you're seeing right here. So here you can see close-up of massive alluvial deposits at the entrance to Afton Canyon, Mojave Desert. So you can see, a person down here for scale. And this is just an example of looking at the desert floors. This is an arroyo. There's many arroyos that have been cut in the last couple of centuries in the desert floors of the southwestern United States. And what they reveal is that the floors, and again, I've got many examples, but in the interest of time, I'm just going to show you one. Arroyos reveal the composition and structure of the desert floor built from massive mud flows. So when you're out there hiking, riding, driving over the desert, a lot of the areas that you're driving over ultimately were emplaced as gigantic water-saturated mud flows and then have subsequently dried up and drained away. And then here's the next one, shows the modern Rio Grande. This is another example of what's called a misfit or an underfit river that's flowing in a channel that's way oversized of the river that's flowing in it. The old view was that, oh, this was created over millions of years for many reasons. Now we know that's not the case, because the oversized channels are all part of a whole suite of these diluvial features that have now been identified. So I'm just going to, again, speed through here. This is Valles Calderas, the largest volcanic caldera in North America. And it's very interesting. It's about 11 miles wide. And I want you to look at this right here, and you'll see it here at about 8 o'clock. There was this canyon leading out of it. And somewhere around the end of the last ice age, in this same window that we're talking about, this whole caldera filled up and formed a lake. And then it breached the wall of the rim of the caldera down here, and that water drained out. And you can see right here, here's the breach point. If you've never been to Valles Caldera in New Mexico, I highly recommend it. It's incredibly beautiful, but it's interesting because the juxtaposition of catastrophic features that created, catastrophic events that created this feature is very impressive. So here was the breach point. It came out this way, and let's see, I should have showing where the water overflowed the rim of the caldera, and immediately below you can begin to see some of the kind of sedimentary features that were produced. This water is not, when you say water, it's less like water than it is almost like a slurry of concrete, completely choked with sediment, boulders, all kinds of things. And here you can see just a cross section. And then as the flows proceeded, there's going to be a hierarchy of various erosional features and depositional. So you'll have slower flows will create the finer grained stuff, and then you've got much more coarse. You can see how the finer grained is sitting on top of coarse material. And then down below at the bottom of the where the the channel discharges out onto the valley floor, you see the creeks are, you can see right here, this is a rounded boulder, indicative of water transport, because water will round off a boulder. My friend Brad Young is standing on it, and so this boulder is 6 to 9 feet in diameter. And if you hike up the Jemez River for miles, you'll see the whole valley floor is choked with these giant rounded boulders. And the modern Jemez River is not moving these boulders. And then you also see things on this scale that are probably easily 1,000 to 2,000 tons laying down in the hollows at the bottom. We'll just keep going here for the sake of it. Okay, so this was down in the Chiricahua Mountains, and so there was what's called pluvial lake Cochise, let's see right here, okay, that once upon a time filled what is called the Wilcox Basin. And the Wilcox Basin is a topographically and hydrologically closed basin in the northern portion of the semi-arid Sulphur Springs Valley in southeastern Arizona. In the past, the Wilcox Basin was intermittently occupied by larger and more permanent bodies of water. These lakes represent former stands of ancient Lake Cochise. So is this sounding familiar now? So what I'm showing you is that we could travel over the whole southwestern United States and find evidence of huge volumes of water, sometimes forming lakes, sometimes forming massive rivers, sometimes standing still, sometimes flowing. But the end result of this is that you soon begin to realize that, yes, huge swaths of what is now desert were once submerged under gigantic volumes of water. As today, no external surface or subsurface sources of water entered the Wilcox Basin. Consequently, the large lakes formed whenever precipitation and surficial runoff within the basin exceeded losses due to evaporation. A prominent shoreline representing a high stand of Lake Cochise circumscribes the basin at an altitude of 1,274 meters. So I went out there, I found that shoreline, was able to then take photos and drone footage and everything of the lake basin. But where there's no lake now, as it says here, how did the lake form? An additional source of atmospheric moisture that could have helped maintain a lake in the Wilcox Basin during the early Holocene may have come from intense rainfall. Perhaps an intensified period of tropical storm activity provided supplementary moisture which maintained the high level of Lake Cochise during the early Holocene. With respect to the early Holocene high stand of Lake Cochise, one conclusion is clear. Precipitation must have been greatly enhanced. So now, what I've done here is I've drawn, and we're only looking at a small part. I mean, I've got hundreds of these references and research that I'm trying to draw together here to paint this big picture, all right? And what does the big picture reveal? Well, the big picture reveals that, yes, there have been these gigantic deluges that literally, you could almost say, are biblical in scale. And North America has been subject to this. And I'm arguing that this is the hardcore evidence preserved in the landscape that ultimately is the source of the same traditions that we opened this conversation with, talking about these amazing traditions, sometimes very detailed, that have come down to us from the native inhabitants of this land. And of course, one of the implications to me is that we should actually be holding these accounts, these mythical accounts, in very high esteem and value, because it provides insight and information that can supplement and complement the information of geological studies such as I'm showing you here. Then, next door to the pluvial Lake Cochise are the Chiricahua Mountains. And I'll just show you a couple here. It's formed of a rock called welded tuff, which is a fairly soft rock which can be eroded quite easily. But what you've got here is thousands upon thousands of these pinnacle rocks, which are called hoodoos. And out here in the distance, right here, let me see, I think in the next slide, let's see, you can see right out here, this was the basin of Lake Cochise, right? I would argue that when they mention surficial runoff, I would suggest then that the same runoff that filled Lake Cochise also did this amazing erosion on the Chiricahua Mountains and left these things like this, and so on. So, again, this is close to the Mexican border. It straddles, it's right on the southeastern border of Arizona. The Chiricahua Mountains somewhat straddle the border between Arizona and New Mexico. It's the one place in North America where you have both cougars or mountain lions and jaguars that cohabit the Chiricahua Mountains. But definitely worth the trip down to see this for yourself. Let's keep going here. There's so much to get into that we won't get into today. But this is very similar type of stuff. This is the hoodoos in Coal Mine Canyon, which is on the Hopi Reservation. I've done tours out there with Robert Dakota and others, and we get Bertram, who is a Hopi storyteller, and he takes us into these places. This is considered to be haunted, and they suggest do not remain after dark. But anyways, if you look there, you've got these what are called hoodoos, which are these spires that you see. And again, this is the result of intense erosion. Also something else, when you have normal erosion, it creates V-shaped valleys. When you have catastrophic erosion, it can create sheer vertical walls. And if you picture this process, imagine You've got an uplifting section of crust. When it uplifts, it fractures, forms fault lines and cracks, right? Now, when you have water flowing over it, the water is always looking for zones of weakness, the zones of least resistance. So what it's going to do is if you have a crack in the bedrock, it will start flowing in that crack. Typically what it does, how many of you know what a slot canyon is or have hiked in some of the, yeah, okay, cool, right. Okay, so now imagine the water getting down in it, and what it tends to do is to erode it horizontally, like this, right? Once the water flows cease, what you're left with is a deep, narrow canyon with sheer vertical walls, not V-shaped. So when you're going over, this is Canyon de Chelly, which is in eastern Arizona, and those sheer vertical walls are an indication that it was probably catastrophic erosion, or maybe a series of catastrophic flows through here that carved this out, and not slow erosion, right? But the thing of it now is, here again, there's no flowing water to speak of in there. And what minimal amount of flowing water, you look at that and you go, wait a second, did this little trickle here form this? And I think the answer is unequivocally no. Here's an example of a freestanding pinnacle rock. So what happens, let's say, picture this, you've got bedrock with multiple cracks and fractures in it. The water is flowing, it starts carving like this. Over here there's another crack or fracture, and it's eroding this way. And if it's branching, what can happen is you'll end up with something like this. See this flat slab of rock here? And see this forming of slot canyons right here, tributaries. And then here you've got remnants of what were former part of the bedrock. And we're going to keep going here. I'll talk about Grand Canyon later. Here's an example of cataracts, dry cataracts up in Utah, out in the along the Green River. They're not being created now. What's happening is the sharp edges of them are slowly being eroded away. They're features like this are basically being destroyed. The modern erosion is wearing down the land. It's rounding off the corners, the sharp edges, and these things will disappear. If you have another hundreds of thousands or even a few million years of normal erosion, these things will eventually disappear. This was created, in my opinion, by extreme water flows that swept over this region of the continent and are no longer operational, and has left a series of dry cataracts. When you look at this, Monument Valley, once upon a time, this was the land surface up here. All of this material between these buttes has been removed. You can look at strata over here on this butte and find its counterpart over here on this butte and this one over here. Something removed all of those, and this general assumption is, oh, it was wind, because wind is blowing there now. Well, when you go up to the Channel Scablands, where it is now acknowledged by geologists that it was water eroded, you find features almost identical to these. For example, compare Steamboat Rock in the Grand Coulee, which is definitely agreed by geologists now to have been formed by catastrophic water flows. And some of the other, in fact, some of the Scabland landscapes are called butte and basin, because there are buttes, just like you've got here, buttes. However, the assumption is here that these are ultimately the product of wind erosion, ultimately. Or water erosion, no, but where's the water? There's no water flowing here. That's not a river there, that's a road. This is dry, arid desert, right? There's an example of a mesa, 900 feet high, just 1 mile in length, right? And here's a topographic map of it. And you can find features like this is very much on the scale of Steamboat Rock up in Washington that was a byproduct of the Missoula flood. Another feature that I would challenge as being formed by wind is one of these, because we can see in several places now where I have traveled, including Grand Coulee, there are rock arches in Grand Coulee that were created by turbulent flowing water. However, if we are now to accept that something like this was created by flowing turbulent water. It challenges a whole lot of sacred cows about geology. But the thing is, I challenge anybody to find me a rock arch or a natural bridge forming anywhere in the world today. What's interesting is this little guy up here that looks like that's the beginning of the process that ultimately leads to a natural bridge or a rock arch. You see this thing up here? So then, let's see here. Since we're in the southeast, I want to end up with this. I'm going to skip some stuff here, as much as I'd like to. Potholes. We talked about potholes. Here's a giant pothole along the St. Croix River that was receiving catastrophic discharges from melting superior lobe of the Laurentide ice sheet. Here's an example of one that's 15 feet wide and about 70 feet deep. Here's one where I'm down inside. Let's see, I'm looking up. Yeah, I took Graham Hancock to this when he was researching Magicians of the Gods. And I'm down in the bottom of the pothole, and he's up there at the rim looking down. You can get a size. Now, this pothole is about 80 feet deep. However, it's about a third to halfway filled up with sediment, so I'm not actually standing in the bottom of the original bedrock pothole. This is created by this. Underwater tornadoes, they've been likened to. Culking is one of the terms. Vortexes that are created in massively flowing catastrophic meltwater floods. And we can actually trace where this discharged from the ice sheet, right up near Duluth, Minnesota. Okay, so here is a gravel pit along the Wabash River in Indiana, and the gravel pit is exposing the fact that there's several hundred feet of catastrophically emplaced sediment. And you can actually see the sweeping currents in here when you're looking at this. Again, I've got to speed through this because we're probably just about to run out of time. But a couple of things that are of interest. You see this kind of vertical-oriented stuff up here? That's loess. And it's a unique type of material whose origins are controversial. Whether it's wind or water emplaced, I think it's both. And in fact, I think that what we're looking at is after the final floodwaters drained away and left all of this stuff, a couple of 100 feet thick of this coarse gravel deposit, this is the stuff that came out of the atmosphere. This stuff was in the atmosphere, saturating the atmosphere while this flooding is going on. And the most likely explanation in my mind, as I've examined probably half a dozen to 10 different outcrops from Mississippi River out to eastern Washington and other places, is that it would have been essentially like a rainfall of mud. And then along that same river, you find these kinds of eroded features coupled up on the embankments, coupled with things like this. Now again, what you've got is a sheer wall, but you've got, picture this, turbulence working against that wall. See, if that turbulence had continued on, you would have had freestanding pedestals here, right? But it stopped and left this what's called the 7 pillars. We got to keep going here. Keep going, sorry that we're missing so much. Now, one of the things that I think was an important phase of the whole deglaciation was forming of this Lake Agassiz, which was a gigantic inland freshwater sea. Now, there are various kind of traditional models of what happened there, but I believe that it was a very quick, very catastrophic melting of the ice sheets. Now, glacial Lake Agassiz, here's another version of it right here. You can see that it dwarfs all of the Great Lakes put together, right? So one of the things that I think is that, and we don't have time to get into this today, but I'll be diving into this. If you watch my podcasts, I do dive into this stuff more intensely. Beckett and I are doing an interesting series where I'm not rushed and we can kind of leisurely go through this material. We're calling it The Big Picture. And I think we've got 5 or 6 episodes now, and we're really focusing on an in-depth, detailed look at this kind of stuff that we're rushing through here. Right here, look at the southern arm of this glacial Lake Agassiz right here is a discharge point. I also brought Graham Hancock there to that catastrophic outburst point of Lake Agassiz. And I think, again, that Lake Agassiz was not something that formed over thousands of years, but maybe literally in less than a year, maybe even less than a month. Why? I won't get into that today. This was a seminal paper, if you want to take a note, G.H. Dury, Misfit Streams, Problems in Interpretation, Discharge, and Distribution. For those of you that do want to take a deeper dive, this is a good paper. Because he's here talking about this situation where you have a very large channel and a very small creek or river, relatively speaking, in that channel, right? And that the modern river or stream did not create the channel. But of course, if you have a mega channel, a mega flood, a mega river, it creates a big channel. It's naturally going to capture any overland flow. And that overland flow, once into that large channel, it's trapped. And it will not ever escape from that large channel until you have equivalent flows again that can reach up to the brim and then overflow. And so, as it turns out, we won't have time to get into that today, but I've pretty much investigated most of the rivers in North America, and almost all of them are way oversized relative to the flows that are in them. And I think I'll show you some examples here. Let's get into some of this. Let's see here. Okay, so some of it is a little bit more subtle, but over the prairies, say from the Great Lakes to the Rocky Mountains, you can see in these Google Earth images here, these streamlined forms. This is formed by sheet floods that are estimated to be 1 to 200 feet in depth and up to 100 miles wide, And what they do is they leave this suite of features that you don't really even notice from the ground. And that's one reason why we're just now really on the kind of threshold of this new understanding of Earth change processes, is because we have satellite surveys now, we have aerial surveys, we have LIDAR, we have ground penetrating radar, we have digital elevation models, things like that we can see things that a few generations ago we couldn't see. So these are just multiple examples of huge flows that came over the prairies. This is just a diagram of what one of the papers by Kehew and Lord, who did a lot of the work on the megafloods over the Midwestern region of North America. And these are all streamlined forms. This is one of the things you look for. And then I've got examples again from Mars, showing you the parallels between gigantic floods on Mars and gigantic floods on Earth. And that's a whole nother story. At some point, I'm going to do a presentation about Mars. But so let's see if we can take this. If you look carefully here, you'll see that in this channel right here, the river. Okay, that's an example of an underfit river, as it's called. And we can keep going and see multiple examples of this kind of phenomena. I'm sorry we're having to go so quick. Okay, here's a great photo. Here's the modern river right here between these rows of trees. And this is the channel. This is the meltwater mega river. This is a lake, right, that now occupies the channel. Here's another one, channel. This is a textbook example of an underfit stream. Note the diminutive size of the modern stream in comparison to the channel it occupies. And many examples of this. Here's another variation of Lake Agassiz where you can see the scale of Lake Agassiz compared to the modern Great Lakes. If you're interested in doing this more, go to Google Scholar, put in Lake Agassiz, and you'll probably get 10 or 12 papers that are not behind paywalls that you can download and read. So this is the kind of stuff that's at the discharge point of Lake Agassiz. This is Graham Hancock here. We had just been out showing him that outlet. It's called, in fact, there's a lake there called Big Stone Lake. And the reason it's called Big Stone Lake is for miles and miles there are these really big stones. And that was from the catastrophic discharge of Lake Agassiz. This is an interesting thing because this was one of my very first early on intimations of something spectacular. I've told this story, but oftentimes without the visual. Right in here is Flying Cloud Airport. This is the valley of the Minnesota River. I was 18 years old and out at a free rock concert, free rock festival up here by the airport. And I wandered over here near this gully and stood there on this bank right here looking out. Bankment is 200 feet high. And let's see here. We can go to a LiDAR view where you can see the full channel here. I was standing right here looking out into this enormous chasm, and right down below, I don't know how well you can see that from here, but the Minnesota River flows right here, and it's minuscule compared to the giant channel that it flows in. And that was one of my first intimations that maybe there was something else going on here. And it sort of marinated in my mind for 5 to 8 years before I finally circled back to it. I probably read Velikovsky or something like that, talking about catastrophic events in Earth history. And I thought back to this day I'm standing out here looking into this huge channel. I got challenged once in the 80s. I was giving a lecture on this, and a geologist in the audience challenged me and said, no, that's millions of years of erosion. And I was pretty convinced that it was not. And I got so irritated at the guy, went and enrolled in geology in college, took a couple of years of geology, got awarded the outstanding student of 2 years over 1,000 other students, apparently because I came in there with, like 5, 6, 7, 8 years already of intensive study, like what the hell is going on here? But anyways, I then learned, because I found papers and studies from a number of geologists that had looked at this, and they called it glacial river warren, and they estimated that its peak discharge, it was more than 4,000 times the volume of the modern Minnesota River. And I've been waiting for the day when I run into that guy again and rub his nose. You remember that argument we had like 30 years ago, 35 years ago? Well, you know what? You lost, I won. But here, you can see this is pretty clear. This is your textbook example of a underfit river. And this is, again, the Minnesota River flowing in a huge channel that conveyed, again, 4,000 times more than the modern river that's flowing in it. I did go back and I found that place where I was at so long ago. But what I realized when I was looking down into the valley again after from 1969 till about 5 years ago, I think, when I took this picture, was that it apparently had been logged over. Not long before I was standing on that bluff in 1969, and it's now completely overgrown, and the evidence of this scale invariant phenomenon was not nearly as obvious. However, if you do look right in here, you'll see a series of giant ripples. And that's a feature of huge volumes of moving water. But this was a beautiful day, and it was great to be back there and to stand there again after so many years and look down. This is a lake. This is not the river. This is a lake, by the way. Let's see. Okay, so then this is showing some of the formations and features of catastrophic, well, it doesn't have to be just water flow. And this is what do they call this again? A Sichilwanen, right? It's a subglacial basinal form, a Sichilwanen with striation. French River, Georgian Bay, Ontario. Note the sharp crescentic rims and primary furrows, like this right here, like this right here. Flows from the lower left to the upper right. Okay, so notice this sort of parabolic form here. And then if you look at this is just like a creek near where I live. And after a heavy rainflow, I went out there and I took some pictures, and you can see exactly those forms right in here. And then, yeah, here you can see, look at this. You see this form right here. You can see these forms. Look at this. Okay, then you go out to eastern Washington, you find exactly the same thing, except on a mega scale. So this is where, important thing to keep in mind. The erosive power of water depends on primarily the velocity. When the velocity is fast, it's more erosive. The velocity of the water depends on the gradient. The steeper the gradient, the faster the water. If you get to a low profile gradient, the water is going to be moving slow. It may not be erosive at all. It may be deposition or somewhere in between. In this landscape, we have relatively slow moving water, and all it's really doing is taking the roughly 200 feet of loess topsoil and smoothing it out, right? But you can see right here, look at this parabolic form right here. It's exactly what we're seeing here in these photographs and what we're seeing here and here. But again, scale and variance, very important in geology. That's why you always have in geological pictures, you have a rock pick or a person standing there. Otherwise, you don't know, are we looking at an outcrop that's 6 feet high or 600 feet high? I'm going to conclude with drumlins because I think drumlins are going to be a key to understanding the nature of this catastrophe. This is an aerial photograph of a drumlin. It's an elongated, streamline type form, but it has a blunt end up current and a tapered end down current, okay? So this water, and see, here's the thing about a drumlin. They only form under glaciers. It's water flowing without a free surface. So there's an overlying glacier that could be thousands of feet thick. So there's this lid that causes the water to flow under enormous pressure. Now, when the glacier comes along, grinds over the landscape, it pulverizes it and creates glacial till, which is the raw material that forms moraines, eskers, and drumlins. But now, picture, in glacial till, it's completely chaotic. There's no structure to see in there because the glacier just grinds up everything. Rocks, boulders, sand, gravel, organic material. Now, you've got a huge subglacial flood coming under the ice sheet, under pressure, and what it does is it shapes the till into these streamlined forms like you see right here. And this is evidence of massive subglacial floods. Here's a section of a drumlin swarm. And in some of the more magnificent and large-scale drumlin swarms, there's thousands of drumlins covering thousands of square miles. And it tells you flow direction because the blunt end, like I said, is up current, the tapered end is down current. So that is a paleocurrent indicator. It tells you which direction the water was moving. And we're going to have to speed through some of this because I think I'm down to, 5 minutes left? What time is it? It's what? After what? So we got a break for dinner. So let's just end up here with, here's our buddy Jerome Lessman, who's one of the world experts on drumlins. Myself and Brad Young are up on the plateau region in British Columbia. Cold as hell out there. Wind is blowing. I have 15 minutes? Oh, okay. Well, I don't have to panic then yet? Okay. Yeah, so we're up there looking drumlins, and this is an example of a rock drumlin from the ground. It's blunt on the upper end, tapered on the downstream end, and they can form, like if you have an obstacle in the flow, this pressurized flow will carve that obstacle, and then it'll create this long tail of debris extending off of the prominence. Does that make sense? I hope. But what we were looking for is we went up there, we were looking for drumlins that was evidence that the source of at least some of the water that created the channel scablands came from the north out of British Columbia and not from the east out of glacial Lake Missoula. Jerome Lessman was a graduate student under John Shaw who kind of first came up with the idea that drumlins were formed by subglacial pressurized floods. His critics savaged him, though, because he couldn't provide a source for the huge volumes of water necessary to create these drumlin swarms, right? They said, well, was it on top of the glacier water formed, called supraglacial? Was it below the glacier, subglacial? And they said, there's no way that you're going to be able to produce the reservoir of water. And in one case, what is called the Livingstone Lake event, it was, the calculation showed that the total discharge of that event was about 84,000 cubic kilometers of water. And his critics said there's no way that you're going to be able to form reservoirs because, for example, let's say when summer comes in a glaciated terrain, the glaciers melt and surface water will pool on the top of the glacier, right? And it'll form, you know, a lake up there temporarily because usually somewhere before the end of the summer, that water will have found a fracture or what's called a moulin. It'll find some access to the bottom of the glacier and it'll quickly drain away. And we know from studies where they put dye in the supraglacial water that it'll percolate to the bottom quickly and it'll discharge under the glacier. Typically within 1 to 3 weeks, you'll see that water discharging from the snout of the glacier. So the critics of Shaw said, well, you're not going to be able to get anywhere like 84,000 cubic kilometers of water pooling up on top of the glacier. You're not going to get it underneath. They cited the fact that, well, we know there's huge lakes under the Antarctic ice sheet, but those lakes are in bedrock basins. They're not being held in by the ice. They're actually in bedrock basins, right? Well, he couldn't come up with an answer. Well, I thought we maybe had an answer, and we communicated with him in a few months leading up to COVID. George communicated, and we were planning an expedition to look at a lake called Lake Nipigon, just above the north shore of Lake Superior, and John Shaw was going to join us. Well, 3 weeks after he responded to our request to join us in this expedition, he responded and said, I would be delighted to join you guys. And 3 weeks later, he passed away. He was about, I don't know, 88 or something like that. Unexpectedly, boom. And then COVID came, so we never have made it to Lake Nipigon. But at some point, I'd like to show you what I think Lake Nipigon is going to suggest to us. Anyways, going on here, we show, this is a quote from John Shaw, we show that drumlins in northern Saskatchewan can be best explained by deposition in cavities formed by erosion of the ice bed by running water. This conclusion is supported by the landform associations of the drumlins, by their relation to the bedrock relief, and by their content of mainly stratified material. And we'll look at this right here. This is the Livingstone Lake drumlin swarm, which is within this circle here. This was the biggie, and this is Google Maps showing the extent of this. Now, these drumlin swarms, or drumlin fields, whatever you want to call them, are huge in some cases, right? And so the question becomes, of course, and I actually agreed with Shaw's critics. I agreed that there was no way to form, whether it's superglacial above, subglacial below, end glacial within, to form reservoirs of the required size and volume. However, what nobody seemed to consider was, is there any force in nature that could cause an instantaneous flash melting? And I think the answer is yes, and I think that's the only solution that we're going to be able to come to explain the origin of drumlins. And I'm going to, yeah, so this was out in the drumlin fields up on the Omak Plateau of southern British Columbia. And I remember taking this picture. I was freezing my ass off because the wind was blowing 40 miles an hour. But I'm going to speed through because I want to show you something here. These are examples of drumlin. Here's a drumlin swarm on the Nechako Plateau up by Prince George. And again, by looking at drumlins and the structure of the drumlins, we can tell which way the water was flowing, right? Because the blunt end is facing up current, the tail is facing down current. So, and here is a overview. This is a drumlin field out here in the Rocky Mountain Trench. And I believe that this was a conduit for waters filling Glacial Lake Missoula. But again, there's so much more we could talk about here. This is, again, the Livingstone Lake drumlin field with your flow direction. Let's keep going here, see what we get into. Okay, so here is, oops, sorry. I want to get to this right here. Okay, so this is Lake Ontario, and down here is the Finger Lakes. How many of you ever been to the Finger Lakes of Western New York? We're looking at potentially doing a tour up that way, and speaking of tours, I think we're planning one to the Azores. Check that out. I think there's 2 tickets left. We're also looking at another tour of some of the Missoula flood region that we haven't visited on tours yet. But let's look here what we got. Let's see. Okay, so here's just south of Lake Ontario. There's a huge, magnificent drumlin swarm. Let me see if I can pull up, the map here of terrain. Okay, let's see if I can get this here. Go up here, yeah, right here. Okay, so what I want you to see here is the Finger Lakes, and if you draw along the axis of the Finger Lakes, they're called Finger Lakes, but what's interesting, they extend radially outward from an epicenter. So hold up your hand like this and imagine that those are the Finger Lakes, and they're radiating out from a point that would roughly coincide with your wrist, right? And that is in eastern Lake Ontario, where they converge. You can see here that they are essentially oriented radially, right? And they were, I believe, carved catastrophically for multiple reasons, which again, we don't have time to get into today. But what I want you to look at is this area up here between the northern ends of the Finger Lakes and the southern coastline or shoreline of Lake Ontario. And when we zoom in, yes. Pardon me? We're not seeing it? Oh. Can you see my pointer now? You cannot. I see it. God, what's your problem? Okay, well, if you look up there, are you coming to the rescue? Oh. Why are you not seeing my That's weird. Okay, well, you're just going to have to use your imagination. But you can see the Finger Lakes, the north end of the Finger Lakes, right? Can you see that? So then if I zoom in, okay, I see what's going on here. So I think I'm seeing something down here. You guys are seeing the static image, and I'm seeing, well, I don't think we're projecting the Google Maps. I think that's just the slide, maybe? That's the slide, so they're not seeing. Okay, why would that be? Well, sorry. But, okay, so the northern end of the Finger Lakes, 2 minutes? Well, what I'm going to, okay.
Let's give this a shot. If we can exit out of that, sorry. Probably want to just exit out of that and then pull up the browser.
Yeah.
Switch to
He's got to change it to duplicate mode now.
Oh.
He's going to take care of that.
Gotcha.
Where's the clicker?
Yeah, we were supposed to do that up here earlier.
I have it back there.
Oh, I got you.
All right, he's going to get you taken care of. Now they can see your full screen now. Just keep that in mind.
Okay. Well, it's still the slides.
Should be able to get out of that.
There's still the slides.
Click on,
Click on this.
yeah.
That's what we
And
need.
then,
So then we do that down here.
no.
Well, we can skip it. I'm sorry.
Get over.
Okay, what?
Let me try something.
You're watching us all up here in panic mode?
Can you see that, Rando?
Yes.
Can you show them?
That's it.
emergency producer mode.
I think it was that guy. I don't know his name, but he's awesome. Okay, so what I was trying to do was show you, okay, so here is the Finger Lakes, and you can see here how they've got this radial pattern. And then when you zoom in right up here, this is what I wanted you to see. Here is this magnificent drumlin swarm. And if you go to the east, to the west, oops. Okay, let's see here. Where's my cursor? Sorry, it looks like we're having problems here because now I'm not seeing this on my screen. Sorry. Well, okay, can we go back to the, let's see. All right, let's just go back to this. We'll continue with the slideshow. So this is what I'm trying to show you, is these enormous drumlins that are between the northern end of the Finger Lakes and the southern rim of Lake Ontario. And let's see here if we can. And then if we go to the west, what you're going to see is the orientation. Notice how the orientation of the drumlins is now southwest to northeast. If you follow the drumlin swarm, what you're going to see is this shifting in orientation, right? And they have the same alignments as the Finger Lakes and are pointing to the same basin in eastern Lake Ontario. Like you can see here, drumlins, and you can see the blunt end here. Hopefully you can see can you see my cursor? Why am I not? Anyways, okay, so I'm just going to have to describe what you're seeing here. So then I'm going to quickly scroll through this stuff, because this is basically what I've got here is evidence. If we had another hour, we'd go through and I'd show you how the whole North American continent bears imprints of these gigantic diluvial currents. And that's the point I'm trying to get. The takeaway here is this phenomena that, yeah, I mean, our Native American accounts were actually quite right on. And here's a good example, though. We're looking here, I'm standing on the rim, the eastern rim of the channel of the Mississippi River. And you can see the modern river out there, and I'm standing up on a bluff that's about 400 feet above the river, and I'm looking 4 miles across at an opposite bluff. And we can show that during the glacial melt-off, that entire channel was filled brim full. And over here, you see a distributary channel, which is where the water was so much that the large channel of the Mississippi couldn't contain it, and it just flowed right out and cut a secondary channel. So here's the takeaway, I guess. The geological evidence totally confirms the idea that anybody living here at the end of the last ice age would have been hard-pressed to even survive. But apparently some of them did. We know that. And they have traditions about, taking refuge on top of mountains. There's even stories about that they survived by building large canoes, which I found rather suggestive. But yeah, so I guess the takeaway here is that I could show you every river virtually in North America is underfit in that sense and carried huge volumes of water. There were sheet floods that flowed over huge swaths of land, drowning and submerging everything in its path. There were some of those catastrophic floods achieved discharges of up to 500 million cubic feet per second or more. Now, to give you an idea of what that's like, if you took every single river on Earth, take every continent, North America, South America, Eurasia, Africa, every river on Earth, put it all together in one flow, it still wouldn't even be 1/10 of some of these flows that we're talking about here. So we're looking at phenomena that was a singular period of time where something really extraordinary happened. You know, I was in this great discussion with Robert today, and I know Robert has some interesting ideas, and I think he's probably right. Well, I think he is right about a hyperactive sun, right? I also think that was supplemented by impacts. I think that we're looking at a perfect storm. They may not have been the same event, but over about a 3,000 or 4,000 year period, from about 15,000 years ago to about 12 or 11 or 12,000 years ago, there was something extreme, or a series of extreme events that afflicted this planet. And what I'm showing you here in North America could be duplicated in South America, could be duplicated in Eurasia. And one of the things that also dates to this series of events is the loss of half the great megafaunal species of the Earth. In North America, 3/4 of all species of mammal over 100 pounds in body weight went extinct. Likewise in South America. The peak of that extinction coincides almost precisely with this flooding. And interestingly, when we find the remains of these extinct megafauna, almost 90% of the time we find them in gravel pits, peat bogs, things like that that were ultimately deposited by water. Floods create big deposits of clay, mud, sand, gravel, boulders, etc. And that's where we find the remains of these extinct megafaunas entombed in these kinds of deposits, or perhaps in the permafrost. If you get up into North Tundra lands, we find them in permafrost, but the same thing appears to be the case there, is that many of these permafrost look like they were the depositional results of gigantic floods. And so in some cases, like you'll find enormous trees splintered and busted up, entombed within the permafrost, which of course floods, if you're talking about 100 million cubic feet per second or more, any forest that it encounters, that forest is completely erased entirely. It's uprooted, and those trees are going to be rolled and tumbled and splintered and busted up, and the end result will be you know, the kinds of things you've got up like in the Alaskan permafrost or the Siberian permafrost. So here's my point, I guess, is that a couple of points. One is that the traditions that we've inherited from the past are worthy of our esteem and honor and consideration in attempting to reconstruct these past events. Also, it's apparent that the uniformitarian paradigm, that everything happens one grain of water, one grain of sand, one drop of water at a time, is pretty much obsolete. And we have to be willing, not that the slow processes don't happen, because they do. We're living in a process of slow erosion. But the thing we now have to realize is that our past is filled with these cataclysmic events. And if we want to truly understand our history on this planet, we have to put our thinking within the context of these gigantic natural events. And ultimately, I would think if we want to really understand what the prospects for our future, long-term prospects for our future on this planet, we also have to consider that there's possibly, very possibly, a cyclic nature to these events. And perhaps by looking at the stratigraphic record, the record of these events, we might be able to discern what the periodicity of this cycle is and get a sense of when might we expect something like this again. Although we will not get the same kind of diluvial floods in the sense that we did back then, because we don't have 7 million cubic miles of additional glacial ice piled up on the continents. So I think that's one reason why many of the prophecies of old would consider that the next great cataclysm might be fire, which brings us back to some very interesting possibilities. However, a tsunami event into an ocean or a major solar event that could cause evaporation, maybe on a mega scale, could lead to pluviation, intense pluviation or pluvial rainfall. So anyways, I think we got to stop, because I don't know about you guys, but I'm getting awfully hungry. Talk of cataclysms always makes me hungry. Appreciate it. Thanks. All right, if you guys beat me out there, just save me a few things, okay? Comments, criticisms, anybody? Yeah. What's your name? Daniel? What is it? Oh, okay, so Daniel just asked a question. Because of where coastlines are now, could there be evidence under the ocean, under the sea? And the answer is absolutely yes. And I would say that the future of archaeology is going to be, a lot of it's going to be marine geology. We're going to be finding evidence of things. Well, I mean, we're already finding remnants of forests that are 200-300 feet below sea level, finding evidence of like mammoths and so forth that were living along the coast during the late ice age, and they're now under 400 feet of water. So the answer, Daniel, is yes, absolutely. Any other questions?
Right here.
Yes.
Hi, Randall. I just wanted to ask, how much isostatic rebound occurred on the North American plate?
Say that again.
How much isostatic rebound occurred on the North American plate?
Okay,
And
so up by Hudson Bay, there are shorelines that are like up to 1,400 feet above modern sea level. So that's an indication, if that answers your question.
And just one more thing, like how catastrophic would that have been for the Azores Plateau?
How fast?
Or like how catastrophic would that have been?
Well, I would think that the geoid is always trying to get to equilibrium. So if you have a rising in one place, you've got to have a depression in somewhere else. And then when the ice mass is growing over the North American craton, it's pressing down. Imagine a beach ball, and you're squeezing it this way, it extends that way. So I think that's one way to think about it. So yes, I think that there would be isostatic compensation along zones of least resistance in the geoid, which would be the continental boundaries. One prominent one, which is the Mid-Atlantic Ridge. So yes, I think you could have, with the 400-foot rise in sea level, and which is creating an enormous amount of extra pressure on the sea bottom. At the same time, you've got an isostatic rise over North America, which actually could induce a lateral movement of the subcrustal material, further allowing the potential of massive subsidence along some of the seabeds, particularly along plate boundaries like the Mid-Atlantic Ridge.
Excellent. One more question right here, Rob. Go ahead.
You had a question. I'm pointing at you.
Well, let me get him first. Stand by.
Oh.
Sorry, we had somebody else. We'll come back to Rob in just a second. Go ahead there. Two more questions.
You mentioned evidence of this across the globe. So we're talking, Yellow, Indus, Amazon, Nile, all those rivers have this misfit thing and this massive flooding?
I heard the rivers. Then what?
Do we have evidence of misfit channels in all the big rivers like Yellow, Indus, Amazon, Congo?
Yes, I don't know as much about the South American rivers, although from what I've seen, the answer would be yes. I've personally traversed probably 150, somewhere between 50 and 100 rivers of all sizes in North America. And some of them it's not evident, particularly where there's a lot of forest and overgrowth and so on. But virtually, if you look hard enough, you'll find the evidence of, you walk 100 yards, 200 yards from the modern stream edge, and there'll be an embankment. It may be overgrown with trees, so you don't really see it. And then you walk the other direction, and you'll find another embankment.
One more question, then we'll go back to George for closing comments. Rob, now go ahead.
Thank you, Randall. You touched on tonight the source of the water flows in the Southwest. I know I've heard you speak on this before, but I'm not connecting where you might be suggesting those water flows, what the source of those might be crossing the American Southwest.
So you're asking about the sources of the water flows in the Southwest?
Southwest, yes.
I would think it has to be rainfall. Extreme rainfall. I mean, think about what happened in western North Carolina last October with 3 days of intense rainfall. Now imagine what could happen with a month of equally intense rainfall. And I think maybe that's where the kind of the perspective we need to look for.
I think that's it as far as questions.
Thank you very much, Randall.
Oh, you're welcome, George.
I tell you, it never stops
Let-
with you, man. Thank you, buddy.
Let's hear it for George. Our man George.